and things. So any doubts from H.C. Verma or the booklet so far? Okay, so we'll continue ahead with standing waves. Okay, so what we had seen last time is that the standard type of organ pipes are open organ pipe, wherein both ends are open. So both ends become pressure nodes, and therefore we have the equation of the fundamental frequency as 1 by 2L square root of gamma RT by M, the frequency of nth overtone as n plus 1 harmonic. Then we had the closed organ pipe, wherein one end is open and one end is closed. So the closed end becomes a pressure antinode, whereas the open end is a pressure node. Okay. And here the frequency of the fundamental is 1 by 4L square root of gamma RT by M, and the frequency of the nth overtone becomes 2n plus 1th harmonic of the fundamental. So we had these, okay, and we had also seen that at the experimental level there is something called end correction, where delta L is equal to 0.6 times the radius of the organ pipe. Okay, so this is the diameter. Then effectively the length becomes L plus delta L. Okay, so these are the formulae and things that we've seen so far. So let's first look at a question involving the resonance column experiment. In a resonance column experiment, okay, a tube of length 100 centimeters is used. Okay, now the first resonance with a certain tuning fork is observed when the water level is at let us say 95 centimeters. Okay. The second resonance the same tuning fork is observed when the level, oh sorry, the level is not at 95, it is at 5. The water level is at 5 centimeters. Okay. So first of all, neglect any end correction over here. So first of all, if speed of sound is 350 meters per second, find the frequency of the tuning fork. Calculate the number of resonances which will be observed. And the level of water in each case. Third, if a tuning fork of frequency double of this particular tuning fork is used, calculate the positions of water level for resonances. Okay, just try this out, and as you're working it out, send me your answers. Okay, let's work this out. Ganesh, I'll explain how this is happening. Okay. So let us say this is our open organ pipe. Okay. So the total length is 100 centimeters. Now we are keeping a tuning fork here of some frequency f, and we are seeing that the first resonance occurs when the level of water is 5 centimeters. So let's say it's here. So when h1 is 5 centimeters, the length of the resonating column will be L minus h1, so that is 95 centimeters. Okay. Now as this resonates, what will be happening here is that this will be, we had to neglect end correction, so this will be a pressure node and this will be a pressure antinode. So we can say that 95 centimeters is some odd multiple of lambda by 4, or it is n lambda by 2 plus lambda by 4, like this. Okay. Now the second resonance, when it occurs, by then the level of water is increased to 24 centimeters. Okay. So there is an increase by 19 centimeters. Now when that occurs, this is again the new antinode, and in between there is no antinode. Okay. So that means my second resonance which is occurring at 86 centimeters, this is 2n minus 1 lambda by 4. Okay. So this is 1/2 wavelength less. So this is n minus 1 lambda by 2 plus lambda by 4. Yeah, exactly. Okay. So from this data you can understand that you just subtract these, n lambda by 2 plus lambda by 4 is 95, n minus 1 lambda by 2, or what you can see in the diagram directly is 86. What you can see in the diagram directly, that this space of delta H, which is 19 centimeters, is occupied by lambda by 2. So lambda is 38 centimeters. Okay. So frequency will become speed of sound divided by lambda. So frequency of that tuning fork is 350 divided by 38 into 10 raised power 2 if we calculate in hertz. Okay. So this is about 921 point something hertz. So now we will see the number of resonances that will occur. Okay. Total number of resonances. So the first one was at 5 centimeters. Okay. The second one was at 5 plus 19, 24 second. Okay. Third one will be at 5 plus 38. So that is 33 centimeters. Similarly, fourth one will be at 5 plus 'Similarly, the fifth one will be at, no, so like this you can see the number of resonances till you reach a situation where you have only quarter of a wavelength. Oh, sorry, I made a mistake in the calculations. Fourth one was correct, but fifth one onwards. So H4 will be 5 plus 47, that is 52 centimeters. Then fifth one will be at 5 plus 56. Okay. So that is 61 centimeters. Then sixth resonance will be at 5 plus 63. Okay. 65. 70 centimeters. That's your sixth resonance. Then seventh one will occur at 5 plus 74. Oh, sorry. Yeah, I'm making some calculation mistakes here. So this is not going to resonate. So in in all there are going to be 5 resonances. Okay. So this is going to be when it is resonating such that this is in the the column is vibrating in its fundamental mode. This is going to be when the column is vibrating in its first overtone. This is when it's vibrating in its second overtone. This is when it's vibrating in its third overtone. And this is when it's vibrating in its fourth overtone. Because in this case, the length of the column which is vibrating now, here, this case, so here the length of the column 95 centimeters is like this. No, wait. There is something wrong in the data of my question. See, what this is showing you here is that here the effective length which is vibrating, that is only 19 centimeters. And that is only a lambda by 2. So this is not possible. This is not possible, no? This length should have been actually half of lambda by 2. So the first resonance should not have occurred at 5 centimeters. It should have occurred at, because 95 is a multiple of lambda by 2. It is basically 5 lambda by 2, whereas it should have occurred at 5.5. So therefore this first resonance would not have occurred at this thing. Okay, so the data of the question is faulty. So through this you actually understand that this data is incorrect. Okay, so now let us, so it cannot happen this way, that if the first resonance is occurring at 95 centimeters, the second resonance cannot occur at 86. This is not possible. Okay, because this will mean that L1 is actually a multiple of lambda by 2 and L2 is a multiple of lambda by 2, but this is not the case actually. So this is actually not happening. This is not happening. Okay. You understanding the point? Okay. So let's approach this question in a different way. Okay. So the first resonance is at h1 equal to 5 centimeters. Okay. Now first thing we can do is calculate the possible values of the tuning fork's frequency. Let's do that first. Okay. In the second case, I will give you a value now. Suppose if the second resonance occurred at 25 centimeters. Okay. First of all, is this possible? Okay. And if so, then the frequency of the tuning fork. Okay. The number of resonances. And third, that if okay, so hope you understood why the data of the first part was faulty, no? Because suppose the first resonance was occurring at 5 centimeters and the second was occurring at 24. Okay, that means the relationship was this, this 95 and 86 are supposed to be odd multiples of lambda by 4, but you will see that's not possible, because 95 is equal to 5 into 19 and 86 is equal to 4 into 19. So they are not odd multiples of some, you cannot express them as odd multiples. So it simply cannot happen this way. Their ratio is 5:4. Okay. So they cannot be of this type. Okay. So that is why the data of this was faulty. Yes, Ganesh, that's correct. Okay. So the first thing you have to understand is that if the first resonance is occurring at 5 centimeters, that means, so this means that 95 centimeters is some kind of odd multiple of lambda by 4. Okay. Because remember, the ends of the tube are node and antinode. So lambda is equal to how much? (380) divided by some odd number centimeters. Okay. So the frequency will have to be V by lambda. Okay. So it will have to be of the type 2n plus 1 into 350 meters per second divided by 38 meters. So these are the possible values of frequency. Okay, so the frequency can be 92.1 hertz. The frequency can be frequency can be and so on and so forth. So this is the answer to the first part. Okay. So second part, what is happening is, yes, what you understood is correct. The second part, for the first height of 5 centimeters, the length of the resonating column is 95 centimeters. So it is okay. But for the second height, we are getting it at 25 centimeters. Okay. So L2 is 75 centimeters, and that is now some next consecutive this thing. Okay, so you can understand that 95 by 75 is equal to how much? The length is decreasing now, so it should become 2n plus. Understanding the length of the resonating column. So this is also faulty data. See, it cannot be next consecutive, because if this is 19 times lambda by 4, the next one, so this is also not possible. You understanding? So this data is also not possible. This means that there is a resonance in between. Okay. So this also is the wrong data. Okay. So this is not possible. Okay. Now let's work out a similar part now. Now if the second resonance is occurred at, let's say, 15 centimeters. Now see, is it possible? Now see, this is the case which is possible. So that is the point here, that you have to be very careful when you are analyzing this. Just the fact that distance between h1 and h2 is lambda by 4 is not enough, because it has to fit that lambda by 4 profile, but it also has to fit that the effective length that is remaining, that has to be consecutive next odd numbers of this thing. No, you understanding now? Because the idea is that if the first resonance is occurring here, this has to fit certain number of half wavelengths. So the second resonance will have to be such that it has to fit, the next consecutive one will have to be such that it fits exactly the next possible number of, in between there should be no other antinode, there should be no other pressure antinode. So you can see that. So now this is, going to this position. So this kind of thing has to happen. So here that's not happening, because this is 19 times something, this is 15 times something, so it's not consecutive. Okay. Whereas when you work out the third part, you will see that's happening. H1 was 5 centimeters. So the length of the column in this case is 95 centimeters. So that is some odd multiple of some lambda by 4. So if the second time it is occurring is at 15 centimeters, the length of the column is 85 centimeters. Now if that's the next possible one, so it has to be the next this thing. Okay, so ratio of 95 and 85 has to be consecutive. So you can see this is 19 into 5, this is 17 into 5. Okay, so this is correct. So 95 is 19 times lambda by 4. 85 is 17 into lambda by 4. So our wavelength correctly is going to be 20 centimeters. Okay. So our frequency is going to be 350 by 20 into 10 raised power minus 2. So it is going to be how much? 1750, is it? So this is going to be the tuning forks frequency. Okay. And now let's work out this part. If we have this of 2 times f, okay, can resonances occur? If so, how many? Whereas you also work out if we have another one which is third multiple of this, again, can resonances occur and how many? Okay, so what is the conclusion about the fourth and fifth part? You will see, I think that in fourth it's not possible. Okay, you cannot have, because we had already discussed that now the frequencies possible were members of this series now. So you can see 1750 is a member of that series, but double of that, which is how much, 3500, is not a member of that series. You see now this one, you will see 1750 is a member of this series. If you see, 1750 is some odd multiple of 350 by 38. Okay, so you can work that out. It is which odd multiple? Oh my god, this is telling me that this is not an odd multiple of that also. Must be. Oh, so I think the only thing here is this is 3.8. Yeah, this should be 3.8 here. That's the difference. Three 80 centimeters is 3.8. So that will make a difference. Okay. Okay. So yeah, you can see that 1750 is an odd multiple of this number 92.1, but the other one is not. Okay. Double of 1750 will not work out to be a possible resonance frequency. So when it comes to the last part of this question, you will see that this is not possible, but this is possible. The not possible in the sense that it's not possible with the first resonance occurring at 5 centimeters and onwards. Okay. Is the question clear so far? You had seen here that the possible frequencies were odd multiples of 92.5, sorry, 92.1. So this had to be a member of this series. It had to be an odd multiple of this. So in this case, you can see this is 19 times 350 upon 3.8. Okay, but this one, so in the fourth part, if the frequency of the tuning fork is double of 1750 and the first resonance were to occur at 5 centimeters, you see this is not possible. Okay, because this would tell us that the wavelength would become, frequency double किया तो wavelength half किया, so it should be 10 centimeters. Okay, so then 95 centimeters should be 2n plus 1 lambda by 4, which will not be the case because 95 centimeters is equal to 38 times 2.5. So this would not give you a resonance of this type. Okay, it would give you a resonance set with different this thing, different first resonance. Okay, so the thing is, if f prime equal to 3.5 kilohertz is used, then first resonance will not occur at h equal to 5 centimeters. Instead, where will the first resonance occur? You can think like this, that instead, okay, what will happen here is that, you can go backwards. You can think like this, that if your frequency is this, that means your wavelength is 10 centimeters. Okay, so your nth resonance will occur when this is quarter of a wavelength, so 2.5 centimeters. Okay, then the next one will occur when this is 7.5 centimeters. Okay, then the next one will occur. So like this, you carry on in that series and see how many members you can accommodate. Okay, so this will become 12.5 centimeters. Like that, the last one will be when, so you have, the possible lengths. Lambda by 4 is 2.5. So lambda by 2 plus lambda by 4 is 7.5. Okay, then 2 times lambda by 2 plus lambda by 4 is 12.5, and like that it is n lambda by 2 plus lambda by 4. So n lambda by 2 is 5n plus 2.5. So we want that this 5n plus 2.5 should be less than equal to 100. So what is the closest number to 100 centimeters which is of the type 5n plus 2.5? So you'll see it is 97.5. Okay, so if you put n as 19, you get 97.5. Okay, so like that you get okay. So this will show you that if this frequency is used, okay, the first resonance would be at a height of 2.5 centimeters. Okay, and that would be where L1 is 97.5 centimeters. Okay, so that one would be 19 lambda by 2 plus lambda by 4. Okay, then the second resonance would occur at 7.5 centimeters height, or the length of the column would become 92.5 centimeters, and that would be equal to 18 lambda by 2 plus lambda by 4. And like that we continue in that series. We'll see that the 20th resonance, I think, right, would occur when the height is 97.5 centimeters. So the length of that column is 2.5 centimeters. Okay, which is equal to lambda by 4. So yeah, counting backwards, this would be the 20th. So yeah, if we use this frequency of 3500 hertz instead of 1750 hertz, then resonance will not occur at this height. Okay, but instead the first resonance will occur at 2.5 centimeters, and we will get these many resonances. So it depends on what the question is asking. The question is asking that is this scenario possible, that the first occurrence, the first resonance is at 5 centimeters, okay, and we are getting a resonant series, then that is not possible for a frequency of 3500 hertz. But a different series is possible, and that different series is this. Okay, similarly, when you come to 3 times 1750 hertz, or 5250 hertz, whatever, 52.5 kilohertz, you will see that the resonance series is possible with heights starting from 5 centimeters. So hope this question is fully clear. Okay. Now, okay. So just to conclude this, if the frequency of the tuning fork is 3 times that frequency, so it is 3 into 17.5, oh sorry, 1.75 kilohertz. Okay, or that is 5.25 kilohertz. Okay, then you will get a resonance at h is equal to 5 centimeters. We will get a resonance. Okay, but this will not be the first resonance. Again, you will understand one thing, because in this case now, your wavelength will have become uh, 20 by 3 centimeters. Okay, so you can see that 95 centimeters will be some odd multiple of lambda by 4, be some odd multiple of 5 by 3. $57. Okay. So this is okay. Hmm. But you'll also see that in this case, um, rather, the resonances will occur for the length of the column, being 100 minus 5 by 4. Oh sorry, the height. Okay, or the length of the vibrating column being 5 by 4, that is lambda by 4, sorry, 5 by 3, my mistake. Okay, then the next one, and like this, the first one will be 100 minus 5 by 3 minus some n minus 1 lambda by 2, or the length of the vibrating column will become n minus 1 lambda by 2 plus 5 by 3. So you get a series like this. So you'll see that this first member of this series is going to be, less than 5 centimeters when you actually work it out. So there'll be more number of resonances. Just replace this lambda by 2 with 10 by 3. So basically you want that this thing is the closest number to 100. I mean, not this, like, so you're talking about the height of the column. So this should be greater than 0. So you will have to find the maximum possible value of n. Maximum value kitna hai, so that this condition is satisfied. So we can, just solve this equation like this, that 100 minus 5 by 3 should be greater than n minus 1 times 10 by 3. So n minus 1 should be less than 295 divided by 10. So n minus 1 should be less than 29.5. Now n minus 1 is an integer. So the closest integer less than 29.5 is 29. So n minus 1 should be 29. Okay. So here this n will become 20. So you'll get 21 resonances in this case. You will get 20 resonances. We started from H1, not from H0. Okay, and this height which you will get will be, so this number is 29. Five by 3. Okay, so your first resonance will occur over here at this height. So it's like h1 is 1.67 centimeters. Then your second one will be this plus lambda by 2, and lambda by 2 was 3.33. So okay, then your next resonance will occur at this. Okay, and like that your 20th resonance will occur when the height has become this or it has become 1.67 plus 19 into 3.33. Okay. My mistake, this was 30. N minus 1 was 29. Okay, so this will be the 30th resonance. Okay, so this will be 29 times this. 29 lambda by 2. So that is 295 by 3. So that should give you this. Yeah. So in all you will get 30 resonances for that frequency of 5.25 kilohertz. Okay, starting with the, the first resonance will occur when the water column is 1.67 centimeters high. So this is a bit of complicated analysis, as you can see, because there is, that number theory kind of thing involved. I mean, it won't be very tough once you get used to it. Okay, so we'll just take a quick break, and in the break, just go through the numbers involved in this, particularly the fourth and fifth case that we have discussed just now, or whatever the third and fourth case, where you're analyzing the, yeah, the third and fourth case where you're analyzing the harmonics possible when this is this much. Okay, so that is 3.5 kilohertz. So you're getting these many harmonics starting from the first resonance being at 2.5, a height of 2.5, and the 20th resonance being at a height of 97.5. Whereas in this case, when it is 55.25 kilohertz, your first resonance is occurring at a height of 1.67. 30th one will occur at a height of 98.33, and this is the series. Okay. So if you analyze this question, all these type of situations will be easy for you to solve. So just take this down and take a break, and then we will discuss. After the break, we'll discuss about beats. Okay, students, let us resume. So hope you also had a chance to go through the values in the previous questions, couple of parts, okay, and understood this properly. Okay. Now moving on to the next phenomena related to sound, because it's a completely different phenomena or different effect, and that is beats. So let's start by understanding by definition what is beats. Beats is the phenomena that we see when there is superposition of sounds from sources of nearly equal frequency, okay, but not identical frequencies. Okay. So for example, if we have one frequency of, let's say, 500 hertz and another frequency of 502 hertz, okay, so f1 is nearly equal to f2, but f1 is not equal to f2. Now we'll also see mathematically exactly how we put the limit to this condition, that is nearly equal से क्या मतलब है. We'll understand that also. Okay. So when this kind of situation occurs, then so this superposition results in the effect which we call beats. Okay, so this results in sound of, you can say, of periodically varying intensity, okay, or loudness, okay, or amplitude, you can say. So this effect is called beats. So this periodically varying intensity of sound that we hear, this effect is called beats. In the physics of sounds, okay, in everyday language, of course, beats means something else, but the connection to the language is that beats is rhythmic or periodic variation. That in general is what we call beats. So here, what is the quantity which is varying periodically? It is the amplitude or the intensity of this the resultant sound. Okay. So let's understand mathematically what's happening. It's quite easy actually. So Ajay, write down the definition, is fine. I mean, just understand the definition. You'll have the notes later. So okay. So now let's understand the maths of this. Okay. So if we have, for example, one source which is creating sound of frequency f1, and another source which is creating sound of frequency f2, and we have a detector somewhere here who's at some distance x1 from this one and x2 from this one. Okay. So the individual pressure wave at the position of the detector due to S1 is, let's say, given by, now just to make things simpler, let's take the amplitudes is same. So P naught sine omega 1 t minus k1 x1, let's say, okay, where omega 1 is 2 pi f1. So in our particular example, omega 1 would have been 1000 pi radians per second, because in that particular example we had taken f1 as 500 hertz and f2 as 502 hertz, if I remember correctly. Okay, whereas and k1 will become, okay, so you have the relation that v, speed of sound, is equal to omega by k. So you can write this as v by omega 1. So that is why now their angular wave number will also be different, because their wavelengths are different, because they are having different frequencies. Okay. Where v is of course speed of sound, so it is whatever medium. Okay. V is common for both of them, and x1 is the path length, as you can see. Now the second source is creating a pressure variation, which is the only thing that is common between the two, let's assume, is the pressure amplitude. That will just make life a little simpler. And suppose the sources are having some phase difference also, some initial phase constant phi naught is involved. Okay, so now the resultant effect, okay, the superposition of the two results in a net variation of pressure of P1 plus P2. So before we get into the mathematics of this, let's just try and analyze this. What we could expect as a in terms of phenomena. Okay. Okay, so now if we try and analyze in terms of phenomena what is happening, you'll understand that these two things that we are adding, they have a phase difference which is time dependent. That is the most important thing. The phase difference is this term minus this term, so it is now omega 2 minus omega 1 into t minus k2 x2 or whatever, plus k1 x1 minus k2 x2, whatever we write it as. So that rest of the term doesn't matter so much, because that's a constant. Okay. So this is all a constant. So the phase difference consists of a time dependent part, okay, and a constant term. So this is like you can write this as a 2 pi into f prime t plus some constant, let's say alpha. So the effective phase difference is varying at this frequency, where you can see that omega 2 minus omega 1 is 2 pi f2 minus f1. Okay, so we'll call that So in this particular case, this is 4 pi hertz. I mean 4 pi radians per second, because f prime would have become 2 hertz. This term is like this. Okay. And alpha is a constant which is simply given by that. So importantly, it's a constant. So now instead of getting into the maths, if you just visualize the phasor diagram, then you realize something interesting, that in the phasor diagram, your first wave's pressure amplitude is like this. In relation to that, your second wave's pressure amplitude is rotating. Okay, that is why you are getting that phenomena of varying intensity. So just visualize this phasor for the second wave's amplitude. So it's, this is your delta phi. Okay, so this is literally in a state of, I mean, if we draw it exactly, you'll see something like this. Okay. So this is in a state of motion with an omega prime which is 2 pi f prime. So you can see that the effective amplitude that you're getting, that is like the chord of this circle, which is all the time changing with time. So that's a very nice way to mathematically understand what's happening. I mean, to geometrically understand what's happening here. Okay. So this is your net pressure amplitude. Okay, it will be like this. So this, so what this shows us is that therefore the resultant wave has a time varying amplitude. Okay, which you can see by formula over there will become 2 p naught cos like this. Okay. Where that delta phi is equal to omega prime t plus some constant. So this is the frequency of f prime equal to f2 minus f1. Okay. So this amplitude varies between 0 and 2 p naught at a frequency of f prime equal to f2 minus f1, which in our particular question was 2 hertz, or in our particular example was 2 hertz. Okay, so that means, we hear a sound whose amplitude or intensity is alternating between loud and soft at a fixed frequency of 2 hertz. So it's a sound not of continuous intensity, but a sound which is like a beat, like a rhythmic sort of variation of loudness with respect to time. So that is why this quantity f prime over here is called the beat frequency. Okay. So we will understand the mathematical equation also that we can derive by adding these two or superposing these two. But all that is secondary. The easiest way to understand the phenomena of beats is just by visualizing this phase diagram, where your net amplitude is like a chord which is continuously varying between a diameter and zero, diameter and zero. So accordingly, the loudness of the sound that you are hearing is going from a proportionality of 4 p naught square to 0, 4 p naught square to 0. So the individual sources were creating intensity of I naught. Then the resultant intensity will vary between 0 and 4 I naught at the rate of 2 beats per second, or every second twice. Once in every second twice, the intensity will vary between 0 and 4 I naught. No, this will be cos. Now here I am using this formula beta that. Oh, acha, sorry. Yeah, the angle between the two is this. So it will be not pi by 2 minus. It will be just be 5 by 2. Yeah, my mistake. The two phasors we are adding now, they are like this. P naught, P naught. Okay. This is delta phi. So I'm using that theorem, that rhombus theorem kind of thing. Okay. That theorem. Yes, Sutit. So I'll just scroll up a bit from the beginning of this beats. Okay. Now this formula that we've derived, now the interpretation that we are getting, I mean, more than the formula, the interpretation that we are getting from the diagram, that we'll also get by mathematics. And for that we'll use the sine A plus sine B formula. Yeah. Because the amplitude is common, so we can. So this is what the phenomena of beats is all about. Okay. And this addition in the last step over here, this is what we have to do actually. We have to do this algebraically, but right now we're just interpreting this from that phasor diagram. Okay, Sudhir, so I'm scrolling down now. Okay, so now let's understand the mathematical version of this. Okay, so the mathematical version of this is that the resultant pressure variation that we are getting is P naught sine omega 1 t minus k1 x1 plus sine omega 2 minus k2 x2 plus phi naught. Okay, so this becomes something like this. Okay, now in this again, what is happening? This whole term is a constant. So let's take it as alpha. I mean some other constant alpha, and this whole term is a constant. So let's think of it like a beta. Okay, and this term now, let's becomes okay. So let's think of that as a 2 pi f into t, where f is the average of f1 plus f2 by 2, which in our particular case is 500 plus 502 by 2. So it's 501 hertz, which is basically something like 500 hertz only. In terms of the pitch of the sound, you won't hear too much difference between 500 and 501 hertz. Hardly any difference. Okay, but this term, this is the important term. This is a slowly varying term. Okay, this is a term which is, so it is pi into f prime. where f prime is the difference of the two. Okay, f prime is f2 minus f1. In this case is 2 hertz. Now a particular example. So with all this further analysis, now you can see that we can write the net pressure variation as 2 p naught. Now I'll bring this term here, cos pi f prime plus beta into sine, sorry, pi f prime t. What is that? Okay. This kind of a term. Now further, when we write it like this, we will separate out this term, because what is happening is this is a term that slowly varies with time. That frequency f prime is not within audio frequency range. It is less than 20 hertz. Okay. So it's not an audio frequency. It's a frequency of, time dependence on amplitude. We'll come to that later. Whereas this f over here is the average of the two frequencies. Okay. So in our particular case, this was 501 hertz. In our particular case, this f prime was 2 hertz. So it's a very slowly varying term. Don't worry about the fact that this is pi f prime and that one is 2 pi f prime, because we are going to convert this into an amplitude. So when we do that into an amplitude, this will become a mod. So the mod cos function has a period of pi, whereas the sine function outside, which is going to be without any mod, that will have a cycle of 2 pi. So it will have a frequency of f. So next thing what we'll do is the quantity in the box bracket, modulus of that we will interpret as our net amplitude. So it is a time varying net amplitude which is having a sound frequency of f, which is f1 plus f2 by 2. And so the audio frequency that you are hearing, the frequency of the sound in terms of pitch that you are hearing, that's more or less 500 hertz. But the difference is that the amplitude of the sound that you're hearing is not remaining constant. It's varying rhythmically with time according to what's happening to that box bracket.
Powering on. Powering off.
Okay, so hope this solving part is clear. You're just using the sine A plus sine B formula here, nothing else. Okay. This one. This order doesn't matter because cos is an even function, as you know. So whether we write a minus b by 2 or b minus a by 2, whichever is positive is fine. So now we will interpret this as, so we will interpret this equation as a sound wave with pressure amplitude equal to this thing mod of 2p naught cos pi f prime t. Plus beta or whatever. No? This is the amplitude, or you can say intensity proportional to 4 p naught square cos square this is the net intensity's proportionality, whereas each individual source produces an intensity proportional to p naught square. Okay, so therefore you can say that the net intensity is 4 I naught cos square of this term. So whether you look at the mod cos function or the cos square function, you can see that the sound wave has a pressure amplitude which is time varying. Amplitude or intensity varying at the rate of f prime, which is f2 minus f1, which in our case was 2 hertz. So that is why this f prime is called the beat frequency. Okay. So if you think of how the intensity is varying with time, the loudness or the intensity is varying with time according to this some kind of a cos square graph. So this is one cycle of that variation. So in our case it is half a second. But that's just the intensity or the pressure amplitude. You can also interpret this as a net pressure amplitude. Whereas the same sound wave now in terms of frequency, it has this frequency. Okay, so now if we want to analyze the graph of the pressure variation with respect to time, that's also something interesting. So this net pressure variation, which is 2 p naught sine, or rather whatever cos, I mean you can convert it to a sinusoidal term also, because there's a phase thing involved. So it is cos pi f prime t. So you can always adjust this beta to make this sine. This thing, if you want to analyze it, where now in our particular example we had taken f1 500, f2 502 hertz. So f was 501 hertz, so approximately 500 hertz. So that is having a time period of 2 milliseconds, whereas f prime was 2 hertz, so that's a time period of 0.5 seconds. Okay, so we want to understand now the graph of the pressure variation with respect to time. So that's also something interesting. Or rather the graph of the volume stress with respect to time, the excess pressure with respect to time. Now this term is varying at the rate of this f prime is 2 hertz. So the actually the cos function will have a time period, will have a time period of this much. This is equivalent to 2 pi into 1. So 1 second. This is the time period for the mod cos function. Mod cos. The cos function has a time period of this much. So let's say this is that cos function. So this would be 0.5 seconds, this would be 1 second, like this. Okay. But this one has a time period that's much shorter. So when we multiply the two of them, this envelops this. So so you can think of it like this, that this function, if you just look at sine of 2 pi f t versus t, this is varying between +1 and -1 very rapidly, with a cyclic time of about 2 milliseconds. Okay, but now if we multiply it with this term, if we now multiply it with this term cos pi f prime t, so we'll have to superimpose this very slowly varying term. So instead of varying between +1 and -1, instead of varying between +1 and -1, your sine function is varying between plus and minus of this. So plus of this function is this one, minus of this function is this one. So now it's like your sine function is varying between the positive of this graph and the negative of this graph. So it starts, so the actual variation of pressure with time is like this. It's like in mathematics, you know how to make the graph of x sine x or x square sine x. X square sine x is it's rapidly varying between the two parabolas of y is equal to x square and y is equal to minus x square, like that. So this is the actual. Okay, so this is corresponding to the 1 upon f, where f is this frequency, whereas this periodic variation is 1 upon f prime, because it's the mod cos function, you can see, so pi f prime. So that's why f prime is the beat frequency. Okay, it is the periodic variation of loudness. Okay, intensity, amplitude, etc. Okay, and you can see that this maximum amplitude is 2p naught. So the amplitude itself varies between 0 and 2p naught in this rhythmic variation. Okay, whereas the frequency of the sound heard, okay, what we in musical terms we call the pitch of the sound, that one is, okay. So this is the beat effect. It is a sound of a certain frequency with time variation, periodic time variation of loudness. This effect is called beats. Okay, now so that's all about beats. Okay, so in terms of formula and application, it's very simple. You have to just remember this thing, that beat frequency is given by the difference of the two frequencies. Just you can take mod, whichever is larger, and the audio frequency or the pitch of the sound or whatever, that is f1 plus f2 by 2 is the average of the two. So this is the frequency of the sound you hear, this is the beat frequency you hear. Okay, now the only thing to understand here is, for beats to be clearly audible, that is to hear the intensity, okay, fluctuating clearly, that is you should hear it as loud soft, loud soft, you should not hear it as an average loudness. Okay, the beat frequency should be less than equal to about 5 hertz. Okay, I mean, this is not a strictly defined term. Some people will say this is 8 hertz, some people will say it is 10 hertz, some people will say it's 5 hertz. But in general, now we don't want the difference of the two frequencies f1 and f2 to be very large. Definitely it cannot be greater than 20 hertz, because then it goes into the audio frequency range. But even when it's in the 10 hertz region, most people, they will hear a sort of average loudness, they won't hear the rapidly varying loudness. But the moment the beat frequency is something like 2 hertz or 1 hertz, you clearly hear the sound's loudness. And it's like you're listening from a system where you're continuously varying the volume knob up and down, up and down. Okay, so this is all about the concept of beats. So we are almost done with the theory part. There is Doppler's effect, which we'll discuss in the next lecture. Okay. So meanwhile, you can complete all problems to do with standing waves, and also start working on problems to do with beats. Okay. Even Doppler's effect, you can start from H.C. Verma by just applying the formula of Doppler's effect, which you can look up. The Doppler shifted frequency in the two cases where source and observer are either approaching each other or separating from each other. But anyway, I'll explain the derivation and the full working of it in the next lecture. So keep it till then. So that's it for today's class, people. Thanks for attending. Oh, Sudhir, you still haven't got the module. I had sent it in the group, I think. Okay, I'll resend it. Okay, last week also I sent it in the group once. Okay. Yeah, Sudhir, tell me, what is the doubt? Oh, Cherenkov radiation. Yeah, I'll send you an explanation. Cherenkov radiation has to do with basically, it has to do with radiation that occurs when there is collision. Okay, at the nuclear level. There's a bit of complex explanation of that. So I will send you a web page and some this thing about it. Yeah. It occurs because of quantum state. during some kind of collision or that kind of interaction, uh, there's a change in quantum state of the colliding bodies involved. And as there's a change in the quantum state, there is a quantum of electromagnetic energy, which is a photon emitted, and that results in Cherenkov radiation. Okay. No, it is actually group velocity. There's difference between velocity of photon and group velocity of uh, set of photons. Now, group velocity for radiation can exceed speed of light, but uh, radiation itself, the photons move at speed of light. Okay, so there is, and that cannot be. That is a absolute postulate of relativity. Okay. So there is something called group velocity, which is a little bit more complex when it comes to electromagnetic waves. Okay, we'll be better placed to discuss this after we have done two things. One is electromagnetic waves and light waves from that, and the other is when we also discuss about a little bit about the quantum aspect of atomic physics. But anyhow, I will send you some basic explanation of it, and maybe at a later date when we have completed these two sections of physics, then we can have a better discussion on the same. All right, Sutit. Particle cannot exceed speed of light, but in fact even a photon cannot exceed speed of light. I was telling you there's some other phenomena called group velocity. That group velocity of a wave train can exceed speed of light, but the photons themselves don't travel at faster than speed of light. And in any case, a photon is not a particle. It is a packet of energy. Okay. A, Traditionally, what we call particles is things which have non-zero rest mass. So even a neutrino is very very light, but it does not come in the category of massless. It has non-zero rest mass, and therefore it cannot travel at a speed greater than speed of light. Okay, you're following my point, beta. So when we talk about that, that Cherenkov radiation velocity is more about group velocity of the wave train rather than the individual photons or packets of energy's velocity, which is nothing but speed of light in vacuum or less than speed of light in vacuum in some other medium. Right. And in any case, information cannot therefore travel faster than the speed of light, because any actual information about the electromagnetic field and its changes are traveling with the photons and not with the group velocity of the wave train. So, okay, Sudhir. So I hope the basic idea I'm trying to explain is clear to you. I will send you some more information about this, but as I told you that we'll be in a better position to understand it after two more topics, electromagnetic waves and then also about quantum nature of the atomic physics and nuclear physics, etc. Okay.